Well, hi, everybody. Thank you very much, Hollis. Appreciate the opportunity to be here this evening. So, yeah, I'm going to be talking about plastic pressure pipe materials for both plumbing and mechanical applications. And I could talk for 8 hours on this, and I used to in a different job, go on and on and on for hours of all kinds of different applications. But for tonight, we're going to keep it to about an hour and focus on some things that are probably most relevant. So as Hollis said, my name is Lance MacNevin, and I work for the organization known as the Plastics Pipe Institute, their building and construction division. I'm an engineer originally from Canada. I live in Virginia now for the last 25 years, and I've been in the pipe industry for the last almost 30 years, since 1993. And I'm an official pipe geek. So I worked for a pipe manufacturer for many years. I've been with the Plastics Pipe Institute since 2015. And I get involved with all kinds of technical committees, but I've been involved with product development and design, code certifications, and things like this. The organization I work for, the Plastics Pipe Institute, it was originally formed way back in 1950 in the early days of plastic pressure pipes with engineers who were trying to figure out, how strong are these pipes, and let's standardize and harmonize our dimensions and our test methods and things like that. So today it's a nonprofit trade association based down in Irving, Texas, and it serves all of North America. And our mission, as you can see here, is to advance the acceptance and use of plastic pipe systems through research, education, technical expertise, and advocacy. So this is part of that. And we are supported by about 170 or 175 member firms. And these are companies that make plastic pipes or the materials or the equipment or the certifiers. They all pay dues to belong to our association every year, and that's what pays for the staff, people like me. Within PPI, if you go to our website, the first thing you'll have to click on is select a division, and we have 5 different divisions. Everything related to plumbing and mechanical falls within the building and construction division. So we probably should be known as plumbing and mechanical, but we're known as the building and construction division, or BCD. And the materials that we represent are kind of shown in this family picture down below. So in alphabetical order, we focus on the pressure pipe materials shown here: CPVC, HDPE, PEX, PERT, PEX aluminum PEX, and polypropylene. And by the way, so we're a nonprofit trade association. We don't sell anything. We're, like I said, we're supported by our members, and a big part of our job is to do education. And to promote the products and teach people how to use them correctly and things like that. So these pressure pipe materials within the building and the construction division are used for the kinds of plumbing and mechanical applications that you can imagine. The ones just all kind of faded in here in the picture. So that's plumbing and water service, fire protection. On the mechanical side, we've got radiant heating, radiant cooling, other kinds of hydronic piping, outdoor snow and ice melting, and geothermal systems. Those applications are served by all these types of plastic pipes, and we get involved with all of those. So that's a bit about me. In terms of introducing the course and getting you ready for what we're really going to talk about here tonight, we're going to first introduce the 6 types of plastic pipes that we'll find in construction. And these are plastic pressure pipes used in construction. So again, alphabetically, we've got CPVC, which we're going to talk about tonight, HDPE, which stands for high density polyethylene, PEX, which stands for cross-linked polyethylene, a newer material known as PERT, polyethylene of raised temperature resistance, a family of materials known as polypropylene. So there's polypropylene pressure pipes. There's also polypropylene used as vent pipes. We're not going to talk about that. We don't get involved with that. And there's PVC pipes, which are both used as pressure pipes and then obviously as drain waste vent pipes. We don't get involved with PVC pipes. There's actually other trade associations that focus on PVC, so that's not us. So what we are going to focus on tonight, though, are the 2 most common types of pipes used for hot and cold water plumbing and hydronic applications with inside homes and buildings. And the way that we know that the 2 most popular ones are PEX and CPVC is this graph here is market data from Home Innovation Research Labs from an annual report that they sell called the Builders Practices Survey Report. And this is basically just asking builders around the country, what kind of pipes have you used lately in the past year? And they also ask, I'm sure, about roofing and windows and all kinds of other materials. But this graph is just on pipe. And what it shows based on this data is when it comes to new construction, residential construction, about 2/3 of all new houses around the country are using PEX or PEX aluminum PEX, which is less common. And the next most common material is the one shown by the red line, CPVC, and then comes copper, and then comes some of the other materials down at the bottom. So we're going to focus on PEX and CPVC, the most common ones. But here's our course outline. And first, we're actually going to talk about polybutylene, which isn't used anymore. Hasn't been for sale for 25 years in North America. But we are going to show a few pictures of that for recognition purposes, so that when you're looking at a house and you see plastic pipe and you're trying to figure out what this pipe is, we'll give you some codes and some markings to look for to be able to identify if it's polybutylene or not. And so that'll be the first part of our outline here. And then we're going to talk about some universal requirements for plastic pipes. And this has to do with health and safety requirements that apply to all kinds of plastic pressure pipes. And then we're going to get into CPVC in detail and talk about its history, its capabilities, the standards that are used for CPVC pipes, some test requirements, and the joining systems, and show lots of pictures. And then we're going to do the same thing for PEX. Talk about its history, its capabilities, the standards that apply, some test requirements, and the joining systems for PEX. There's lots of different fitting systems on the market for PEX, so we've got pictures of them all that will show so that you know how to identify them. And then at the final part, we'll talk about how to access some industry resources. And that's basically, I'm going to give you a very quick tour of our own website so you can find some of the really important information that's on our website. Again, it's all open to the public, it's all free, and a lot of good resources out there. So that's the plan. And we'll start at step one, which is polybutylene piping systems. And again, this is a bit of a trip down memory lane here. Polybutylene systems, they were introduced, and a lot of you are aware of this, probably better than me, but these systems were introduced way back in the 1970s as an alternative to copper. And people loved the flexibility, the fact that it came on a coil. You could have longer lengths with fewer joints and just bend the tubing around trusses, for example, and other kinds of obstructions inside the building. And it was just faster to install and less expensive than copper, even back then. This map is not ours. This map came from some lawyer website. And this map, the darker blue equals the states where polybutylene was more likely to be used. So a lot of you tonight are probably in some of those states and have come across this quite a bit. So you probably also are aware that by the 1980s, some of the polybutylene systems already were experiencing some failures. And most of those failures were called premature oxidative failures, where the product became brittle and then would fail. Most of the early failures were actually in the fittings. And the gray plastic fittings that were used from the beginning with polybutylene were not actually made of polybutylene. The gray plastic fittings were made of a material called polyacetal. And the chemical code name for that is POM. Which sometimes may be marked in those fittings. And it turns out that polyacetal was just not very resistant to chlorine at all. Hot chlorinated water, cold water, no problem, but hot chlorinated water, it's a problem. And the fittings would start failing quite prematurely. The standard for those fittings is called ASTM F845. So if you're ever looking at one of those fittings and you're trying to identify, is this a polyacetal fitting? If it is, it should be marked with F845 on it. So here's just kind of a close-up of a couple of fittings in one of these systems. So these are crimp ring style fittings. So the copper rings are the crimpers. A tool will be used to crimp those copper rings over the tubing, compressing the tubing over ribs in the fitting. So it's a good design of fitting, and the fittings themselves were strong enough and everything else. But again, the problem is if they were attacked by the hot chlorinated water, then they would start to oxidize, which is kind of like you getting a sunburn. If that's ever happened, basically from the fittings perspective, if you sliced one in half and looked inside, you'd see kind of a white chalky surface inside if it's truly being attacked by hot chlorinated water. And that chalky surface allows some of the material to dissolve into the water and wash away. but it's really is kind of breaking the molecular bonds between the material. And even if it's not washing away, it's losing its strength and getting very brittle. And especially for an elbow or a T, if there's any kind of stress on the fitting, they could just crack apart and break apart, and you'd have a big gusher kind of leak. So a lot of those fittings have already failed up till now, and have been replaced because they just wouldn't have lasted this long in a lot of cases. So what the industry did then when those fittings started failing is they developed copper crimp fittings. So in this case, the whole fitting was made of copper or brass, but copper was really popular in the beginning. And those fittings were made to a different ASTM standard called F1380, and they were good. The material, the copper was fine, and the copper crimp rings were fine, and the compression, the seal was fine, and they were great, unless you're in a place where copper actually gets attacked by the water. And there's a lot of those places around the country where copper does just get attacked by the water, which causes all kinds of different types of corrosion inside the fittings. So then what the industry did to try to eliminate the amount of fittings in the wall is they came up with home run plumbing systems with centralized manifolds accessible normally in the mechanical closet where the water heater was, where you'd run a dedicated piece of tubing, either 3/8 or 1/2-inch tubing, directly from that manifold to each outlet or fixture. So directly to a shower head or a shut-off valve below a toilet or a sink. And therefore, it would be a continuous piece of tubing inside the wall from start to finish with no actual fittings. So therefore, you're completely eliminating the risk of fittings inside the wall because there is none. And you've probably seen lots of manifold systems out there, and they're also known as home run plumbing systems. It's a lot like electrical wiring from a circuit breaker. But there were still failures, and even with good fitting systems or even with no fittings inside the wall, sometimes the tubing still failed itself. And without getting out into all the details, some of the polybutylene that was used was just not that chlorine resistant. A lot of it was great, and it all could have been great, but some things were done in the industry that ended up being some, let's say, less than perfect materials being used for polybutylene in a few different cases. And then in some cases, the installers just didn't know how to deal with the material properly, and they would scratch it or gouge it during installation or kink it and then straighten it up with a pair of vice grips and put it in service. But that damage would sink into the tubing over time and lead to some stress points that eventually would fail. So some of the polybutylene tubing definitely has failed, is failing, or will fail in the future, but not all of it. So you're probably all aware of the very large lawsuits that were settled. This goes back to the mid-1990s and the late 1990s. So some of the biggest lawsuits for class action material lawsuits ever were about polybutylene tubing. And the companies involved with that were Shell Oil, that made the polybutylene resin itself. They didn't make the tubing, but they made the material. And then two other companies, one called Host Celanese, a European supplier. They made the polyacetyl material. And then also DuPont made the polyacetyl material of a different brand. So those three companies ended up being involved with this lawsuit and ended up paying out probably close to $1 billion in different kinds of settlements around the country for pipe replacement. So to help identify these products, here's another kind of a close-up of the tubing. From left to right, the markings that you see, Quest was a brand name. US Brass was one of the manufacturers of the tubings, and their brand name was called Quest. So that's marked on this tubing here. That's nice that you can see the brand. PB2110 is a material code for the actual type of polybutylene material that was used for the tubing. And that's the material that was allowed to be used for hot and cold water tubing. The NSF-PW, that's a mark that shows that the tubing was tested and certified for drinking water safety. So the PW means potable water. So, and it was tested by the organization known as NSF in Michigan. And then ASTM D3309, that was the ASTM standard for polybutylene tubing. So this tubing here, it's well marked, it's well identified, and we know exactly what this was. Now there was other polybutylene tubing used for other purposes as well. Water service line was a popular application for polybutylene. And in fact, in my house where I am right now, my house was built in 1993. And I know for a fact it has polybutylene water service line. And in fact, this picture is a picture of one of my neighbor's polybutylene water service line that failed a few years ago and had to be dug up. So I went and stole some of his old pipe as it was being removed to take a look at it. And in this case, the pipe is just a cold water service line pipe. It didn't fail because of chlorine in the water. It actually failed simply because where it was connected to the curb stop in the meter box, it wasn't backfilled very well. And with all the movement of the ground over 25 plus years, and eventually there was scraping and gouging in the pipe, and it eventually just cracked the pipe. The pipe did become less flexible over time, and all the movement at that joint by the valve, it just couldn't take it anymore. And then one day a crack opened up and it started leaking, and the water department called the homeowner and said, "You've got a leak, fix that or else we're turning your water off." AWWA C902 was the standard used for polybutylene for water service pipes. But as you can see, this is also marked with PB2110, the material type. And there's even a date code on this piece of pipe. So this pipe was made in June 27th, 1992. And it lasted until about 2018, I think is when my neighbor's service line failed. And that's when I got this sample. So a good 25 years or so. And so the pipe for my own house is 29 years old. It's still going strong. And I have no plans to replace it unless it ever fails on its own. And then I have a coil of PEX in the back closet that I'm going to use as the replacement. And we'll talk about PEX here later today. Another use for polybutylene was as radiant heating tubing. So radiant floor heating has been around for a long, long time. And people used to use polybutylene in North America. And the product was very suitable for that application. You see this radiant heating tubing here coming off a manifold. It's also marked with the ASTM D3309, so it's the same standard. The difference is this tubing has kind of a red shiny coating on it, and that red shiny coating would have been an oxygen diffusion barrier. I'll explain a little more about that later in the presentation when we're talking about PEX. In this case, this tubing could easily last for 50 years. I don't know how old this picture was or how old this tubing is, but there's a very good chance it could last for 50 years or more, because most of our radiant heating installations, if they're well controlled and well installed, don't need to run at very high temperatures, maybe just 120 degrees Fahrenheit or less on cold winter days. So this tubing could easily be there for 50 years or more and be completely okay. There is a document on the PPI website that you can access, because what we're going to be talking about later this evening is cross-linked polyethylene, or PEX, and PEX is a lot better than polybutylene. And in fact, we even have a PPI document on the website, looks just like this, called TN31, that explains to anybody who's interested the differences between PEX and polybutylene. The first is that PEX tubing is cross-linked. And I'll explain that with a picture in a few minutes. But what that means is when you have a piece of PEX tubing, most of it is the same molecule. All the molecules of polyethylene, or most of them, are actually cross-linked and linked to each other. So a piece of PEX tubing is kind of like a chain link fence with all these molecules connected to each other. So that makes the tubing both more flexible, like a chain link fence, but also has a lot of toughness and a lot of resistance to scratching and gouging and cracking. PEX tubing, it also has a thicker wall than polybutylene did. It's SDR9. I'll explain what that means in a few minutes. But it means the wall thickness for a given diameter, it's about 22% thicker than it was for polybutylene. So that makes it tougher. And nowadays, ever since the year 2002, it's been a mandatory requirement that all PEX tubing for water be tested for chlorine resistance. And that was not a requirement for polybutylene. And it turns out polybutylene was slightly resistant to chlorine, but not good enough in many, many cases around the country where we use higher levels of chlorine. So now it's a requirement for PEX to prove that it's resistant to chlorine, but that wasn't even a system in place for polybutylene back in the 80s and the 90s. And then the PEX systems, when we show PEX fitting systems later tonight, we're going to show lots of different fitting systems. A lot of them are made of plastic. They're not made of polyacetyl. They're made of different plastics known as polysulfone or phenyl polysulfone, which are really expensive plastics, also used in space applications and automotive applications. And they're safe for drinking water, and they're resistant to chlorine and extremely tough. And they're far beyond what the polyacetyl fittings were. And then finally, for PEX systems today, like all plastic pipes, the quality control programs are far more stringent. All these companies have multiple third-party certifications. And part of the third-party certifications with agencies like NSF or CSA in Canada or IAPMO includes annual retesting of everything, and then normally 3 or 4 surprise unannounced inspections of your plant each year, where the inspectors from those agencies just show up and take random samples back to the lab and do retesting to make sure that everything is as good as it was in the beginning. So companies, not only do they have no incentive to cut corners because of our legal system in the US, they're also highly regulated and highly controlled so that they couldn't cut corners if they wanted to because they would get caught. So the industry today, it's much better than the industry was 25 years ago. And just to kind of summarize the polybutylene topic, the first thing that we said is that polyacetyl fittings were susceptible to hot chlorinated water. So that led to a lot of their failures. Some of the polybutylene was also susceptible to hot chlorinated water. There's a lot of polybutylene tubing that is perfectly okay in cold and hot water plumbing systems and will easily serve out a life of 50 years. But it all depends on the quality of the tubing, how nicely it was installed, whether or not it was abused during installation. And it also depends on, the temperature of the water system it's in and how much chlorine is being used in that town or by that utility. So some of the polybutylene will be around for 20 more years, whereas other polybutylene, it won't. In fact, there could be a failure tomorrow or somewhere of polybutylene somewhere in the country that's just reached its end of life. So that's about it on polybutylene, and I guess we'll take questions via chat. The next thing I was going to then touch on, we're calling this part an introduction to plastic pressure pipes, and we're going to just touch on some terminology that applies to all different types of plastic pressure pipes, just so you understand kind of the rules that apply to the industry and what some of these terms actually mean. And the first thing we're going to introduce is the topic of the standard dimension ratio. And the official definition is given here. It is the ratio of the outside diameter to the wall thickness, calculated by dividing the average outside diameter of the tubing by the minimum wall thickness. Now, when it comes to PEX tubing that we're using for hot and cold water plumbing, it's all SDR9, and that would be marked on the tubing, and that means that the wall thickness is 1/9 of the tubing. When it comes to CPVC tubing, that material is actually a little bit thinner. It's an SDR11. So the wall thickness is 1/11 of the outside diameter because CPVC is actually a stiffer, stronger material than PEX. So you don't need as thick a wall as PEX for the same pressure rating. And then if you ever see CPVC fire protection pipe sprinkler systems, that's normally SDR 13.5. Again, it doesn't need to be as thick because it's under constant pressure, but it's cold water and not hot water in fire protection systems. The important part about having a standard dimension ratio, so in other words, as the diameter gets bigger, the wall gets thicker, is that each diameter of the pipe type has the same pressure capability and the same pressure rating. So the example shown here is if you looked at PEX tubing, whether it's 1/2-inch PEX tubing, 1-inch or 2-inch PEX tubing, it all has the same SDR9 wall thickness ratio, and it all has the same pressure rating. So in this slide here, you can see a photograph of 5 different diameters of PEX tubing. It's all SDR9. So that means the wall thickness is always 1/9 of the diameter. And again, the benefit is that all the diameters have the same pressure rating. Here is a close-up of CPVC tubing, commonly used in residential plumbing. And this is SDR11. Again, the wall thickness is 1/11 of the diameter. So that's just kind of a terminology from the plastic industry that we thought you'd want to know. The other thing we want to touch on is a universal requirement has to do with drinking water safety requirements. And it is a requirement by state law and by our plumbing codes, Uniform Plumbing Code, International Plumbing Code, National Standard Plumbing Code, Canadian Plumbing Code. It's a requirement of all the codes out there that any of the pipes or fittings used for hot and cold water must be tested and certified to this standard, known as NSF 61, or the full name is NSF ANSI CAN Standard 61, toxicological evaluation for materials in contact with drinking water. And I won't get into all the details of how they do that testing. It takes about a month and a half to do the test on a given pipe or fitting, and it costs about $15,000. And it's a very stringently done test. And what they do is basically they put super clean, purified water in a pipe or fitting, and then they leave that water there for a little while, and they take the water out to see if the water extracted anything from the tubing or the fitting that could potentially affect human health. And they test for hundreds and hundreds of chemicals that could come out of plastic. And only the products that pass that test get to have the letters NSFPW on them, or the code NSF61 marked on them to show that they've met this requirement. And this is a mandatory requirement. It's not optional. One other kind of universal requirement has to do with the pressure rating of both CPVC and PEX tubing. Both of these products, and this is called out in some of the codes, that they must be rated for pressure of 100 PSI at 180 degrees, and those are continuous use pressure ratings. So the products go through what's called long-term hydrostatic testing in laboratories, years worth of testing, literally sometimes more than 2 years worth of testing at elevated temperatures and pressures to be able to predict that these products should be able to withstand 100 PSI at 180 degrees continuous temperature for 50 years or more. And that is the expectation of today's plastic piping products. And then, of course, when it comes to the benefits of plastic pipe, like why are we even talking about plastic pipe? Why would people want to use plastic instead of copper? Obviously, it's the cost. It's a lot less expensive. It's a lot easier to install plastic because of the flexibility, especially with PEX versus copper. But there's lots of other costs as well in terms of the products being smoother. You don't get mineral buildup. It's better for the planet to make plastic pipe than it is to make copper. Just look up a copper mine and you'll see what it takes to actually extract copper and produce it and convert it into tubing. The plastic tubing, it's a lot less expensive. Obviously, it's not going to corrode. Corrosion is impossible, so that's a big deal. It can withstand really high velocities. It can withstand surge pressures when you have fast closing valves, like at a washing machine or an ice maker. So the plastic products can actually absorb those surge pressures, so there's less chance of water hammer. And they're general insulators, inherent insulating properties apply to both PEX and CPVC, so they actually reduce heat transfer. So there's a lot of benefits to plastic, not just being less expensive, which is a good thing, but all kinds of other functional, practical benefits as well. So now we're going to get into the details of each of these materials, and we're going to start with CPVC piping materials. And it says here we're going to focus on CPVC tubing, pipes, and fittings. And when we say tubing, that means a copper tube size product. When we say pipe, that means an iron pipe size product. So residentially, you're always going to find the products that are copper tube size, meaning they have the same outside diameter as copper. But in commercial plumbing systems, you would be finding more the iron pipe size, IPS pipes. So essentially, they're the same products, but slightly different dimensions between a tubing and a pipe. So we're going to talk about the history, the configurations, the advantages, the capabilities, the standards that apply to these products, some of the test requirements, the markings that you should see, the joining systems, and a little bit on chemical compatibility. So first of all, introducing CPVC. What it is, it's a PVC material that has been chlorinated via a free radical chlorination reaction. That's what the chemists tell me to say. I don't know exactly what that means. I'm a mechanical guy, not a chemical engineer. But basically what they're doing when they make CPVC is they start with PVC raw material and they add an extra chlorine molecule to it.
Still listening?
Yeah.
I'm still listening to your thing because you're snoring really loud.
Well, no, I'm listening.
So that extra C in CPVC really does make a big difference. It makes the product able to withstand extremely high temperatures and higher pressures and gives the product other better properties as well as compared with PVC. It's more expensive, but it is a better product. And PVC is not approved for hot and cold water distribution inside a house, but CPVC is. So this is the product that we're talking about here. And it's actually been around for a very long time. So CPVC, like I said, it's rated for high temperatures. The tubing is rated for continuous operation up to 200 degrees Fahrenheit. It can actually withstand much higher temperatures than that, but 200 degrees Fahrenheit is as high as the markings go for safety. But it's been around for a very long time. In fact, B.F. Goodrich, which was a chemical company and still is, They actually developed CPVC materials way back in the 1950s, and they made the first CPVC pipes in the mid 50s, and then sold the first CPVC plumbing system in a house in Ohio, I think it was, or maybe Indiana, in 1959. So that's more than 60 years ago now, and that house is still being monitored and still in operation. So it's been around for a long time. It's not that new. CPVC was then introduced for fire protection systems in 1985. And again, the alternative there was copper or steel, which would corrode, and CPVC wouldn't corrode. So it was a huge benefit over the metal pipe systems for fire protection systems. So this is not a new material. It's been around for a long time. And there's three different colored pictures shown on the bottom. The orange is typically the version of the product that's used in fire protection. The goldest version is usually the version made in copper tube size dimensions for residential plumbing. And then the grayish product is the one that's usually made in the iron pipe size dimensions for commercial plumbing or hydronics or other kinds of industrial applications. Essentially, it's all the same product, but slightly different versions of CPVC for the different applications. In terms of configurations, this is not coilable. This is not off a flexible roll. It is provided in straight lengths. The copper tube size diameters go from 1/2 to 2 inch, and they're all SDR11. And then the iron pipe size diameters go from 1/2 inch to 24 inch. And you can get the IPS materials in Schedule 40 or Schedule 80 or several different SDRs. And then you get obviously the different fittings molded for the right size. The material code for CPVC for plumbing applications is either CPVC 4120-05 or CPVC 4120-06. Slightly stronger material. And those are the material codes that you would actually see in a piece of CPVC pipe or tubing. In terms of what the product is capable of, without getting into all the nitty-gritty details, there's actually a document you can get on the PPI website called TN62, which kind of describes a lot of the detailed capabilities of CPVC in terms of its chlorine resistance, its resistance to chemicals and high temperatures and high pressures. And it really is a very versatile, fairly amazing material in terms of it's not very expensive at all, but it can be used for a lot of different applications. And like I said, with over a 60-year history now. When it comes to the standards, there are a lot of different ASTM standards for the different versions of CPVC. So this list looks a little bit messy here. But on the residential plumbing side of things, the copper tube size version should always be marked with ASTM D2846. That's the first standard shown on this list. And that standard number should apply to the tubing and the fittings used in residential plumbing. Once we get into the iron pipe size versions, Schedule 40 and Schedule 80 types, then for some reason, there's lots of different standards specifically for the different types of fittings or specifically for Schedule 40 and 80 pipe sizes or the IPS sizes. There's this big list of individual this list of individual ASTM standard numbers here. So if you picked up a piece of gray CPVC pipe, it could be marked with F438 or 441 or 442, depending on exactly what dimension scheme it was produced according to. In terms of the actual markings then, this is an image of CPVC tubing, and the markings that you should see would always be the size, the diameter, like 1/2 inch, the wall type, and that is SDR11 in this case. The manufacturer's name or their trade name should always be there. So the name could be Charlotte Pipe, or the trade name could be a name like FlowGuard Gold, which is a trade name of the actual CPVC material, or it could be the company name Spears. There's different companies out there that make CPVC pipe and tubing. The ASTM standard number is going to be marked on there, D2846. The pressure ratings at both 73 degrees and 180 degrees will be marked on there. The material designation, like I said, CPVC 4120 would be there, and then certification symbols from the laboratory that actually is testing and certifying this product. And there could be 2 or 3 of those. It could be NSF, it could be from CSA, it could be from International Code Council. There could be a whole bunch of different certification symbols on the product to reassure the customer that this product is very well tested and quality controlled. And then you'd find most or some of those same markings on the fittings as well. Not as much because they're smaller, but a lot of the same markings will also be in the fittings. When you come across CPVC pipe, the markings will be similar, not exactly the same, but very similar. The main difference is the ASTM standard number would be different if it's an iron pipe size version, but otherwise most of the same markings would be on the pipe. So now let's move into CPVC joining in terms of how this is connected. And there's really four main types of connection or fitting systems for CPVC. And those are known as solvent cement, push fit fittings, grooved mechanical fittings, or flanged connections. The second two are not likely to see in a residential application, but more in some sort of commercial application. The most common way of joining CPVC is with solvent cement. So this is a liquid that you get out of a can and you brush on the outside of the pipe and the inside of the fitting and join them together. The important thing to point out, though, about solvent cement joining is it is not glue. The first image here is an image of how glue works. Glue actually holds two things together by being a sticky layer in between. With solvent cement, you're actually welding the two parts to each other. So the liquid in the solvent cement actually dissolves the outside of the pipe and the inside of the fitting. It melts them for a little while until the solvent evaporates. And then the molecules actually from one part flow into the other part, and then they join themselves to each other. So that's the basic principle of solvent cement. So here's an image here of somebody just painting the outside of a piece of pipe with the solvent cement. And then they would do the same to the inside of the fitting and then push them together and give them a quarter turn and let them set up for a little while before they put them into pressure. Here's just an example here of some solvent cement itself in a can. So there's a bunch of different manufacturers of this, and there's a few different colors out there. Sometimes it's a one-step, meaning the cleaner and the cement is in one product, and sometimes it's a two-step, meaning first you have to prime it to clean it, and then you use the cement itself. In terms of what these fittings look like, here's an example here of different types of fittings. You can get threaded adapters with metal ends as part of the fitting to allow you to do a connection, maybe to a water heater or something. You can actually get molded manifolds for plumbing, molded out of CPVC, and then all kinds of elbows and T's, 90 degrees, 45 degrees, caps, plugs, couplings. There's a pretty big range available. Another way of joining CPVC is using push fit fittings, and you probably recognize these as SharkBite fittings. SharkBite is one brand of these push fit fittings, but there's other brands of them as well. They were originally developed in Australia about 25 years ago, and they work just as well in CPVC as they work in copper because both products have the same outside diameter. And you don't have to do much to prepare those CPVC. Just give a good clean square cut, make sure there's no burr on the end of the CPVC, and then just push it into the fitting. Follow the instructions, and you'll have a good secure joint with those fittings. There are grooved mechanical fittings sometimes used with CPVC. You're probably familiar with Victaulic style fittings. You're not likely to see these residentially, so I'm just going to move on for this now. And the same with flanged fittings. And a lot of commercial plumbing systems, they'll put a flange in the end of the CPVC pipe to allow the pipe to be bolted up to a valve or a piece of steel or something else. Not likely to see residentially, but commercially, you could very well see a lot of flanged connections out there. So those are the four main fitting types for CPVC. And again, by far the most common is going to be the solvent cement type. That's probably what's used at least 90% of the time. Very secure. One thing to know about CPVC is that it is sensitive to some types of chemical contact. And some of the types of chemicals that will affect it negatively, you might not imagine. But they've learned this the hard way. But companies like Lubrizol, Lubrizol is a big company that makes most of the CPVC resin out there. And what they've done is they've actually done compatibility testing with almost any chemical you'd ever find on a job site. And they publish the results. So they make this really obvious and easy to find. They provide a lot of training to the installers to make sure the installers don't make mistakes and put incompatible chemicals on the CPVC. Because if they do make a mistake, then they can actually damage the product and it'll get weak over time. So the best way to learn more about whether or not a given product is compatible with touching CPVC if it's okay to be touching it, is just to go to their website. So there's a link here. You can just go ahead and Google the letters FBC system compatible, and then you can search for different types of products, whether it's a fire stop product, you want to make sure that's compatible, or some other types of sealant or some other sort of chemical on a job site, and just go ahead and do the search to see if it's compatible. And there's even an app for that. So in the App Store, you could even download Lubrizol FBC and check their literature. That's assuming it's a Lubrizol product. The other major manufacturer of CPVC is called Spears, and you'd have to go to their website as well to check compatibility with their product because it might not be exactly the same. So that's going to wrap it up on CPVC, a pretty quick tour of CPVC, but we want to save time for PEX as well. So now we're going to move on to our section on PEX. And we're going to kind of introduce PEX in the same way we did with CPVC, give an introduction, the history, configurations, advantages, capabilities, standards, markings, joining systems. And there's not much to say about PEX compatibility at the end here. There's not many chemicals on a job site that would damage PEX. So very little to say. So at the beginning, though, to explain what is PEX, the official definition is that it is cross-linked polyethylene. So you're probably very familiar with polyethylene in pipe form, water pipe as service line or geothermal pipe. So cross-linked polyethylene is a polyethylene material which has undergone a change in the molecular structure using a chemical or physical process during manufacturing, whereby the majority of the polymer chains, that means the molecules, are chemically linked. So on this image down in the lower right here, basically what that's trying to show is two long polyethylene molecules, which are big, long hydrocarbon chains. And when you make PEX, you actually link those polyethylene molecules to each other. So it's kind of like the difference between a picket fence, where you have all these parallel boards in a picket fence parallel to each other, versus a chain link fence, where you have all the wires woven into each other. You're having these extra bonds, but it actually doesn't make it stiffer. It actually makes the product more flexible because of the spacing between the molecules that is consistent. And there's lots of other benefits that PEX has versus polyethylene, but the biggest one is it withstands high temperatures. And PEX was actually invented, let me go to my next slide here. PEX was actually invented in the 1960s and first put into commercial production in 1972, happy birthday, 50 years ago, for radiant heating applications with hot water going inside the tubing, inside concrete floors throughout Europe. And now we do a lot of radiant heating over here, but it was very common in Europe in the 1970s, and PEX was the material developed for that purpose. So it's always been used as a hot water transfer pipe. It was then introduced into North America in the 1980s. And in fact, the first ASTM standard for PEX tubing was published in 1984. So that's almost 40 years ago now. So it's been around quite a while. And PEX tubing systems are approved and used in North America for water service line, the hot and cold water plumbing, fire protection, radiant heatings, outdoor snow and ice melting, geothermal ground loops, and other applications as well. And the common types of PEX in terms of the markings you would see are shown here. It's always going to have the letters PEX on it, and then it's going to have a 4-digit code. And those 4 digits actually identify different properties of the PEX in terms of its chlorine resistance and UV resistance and its long-term strength. They're called the material designation codes. And we won't get into that in great detail here, but there's a PPI document you can read that'll explain those codes. So in terms of the configurations for PEX, it's available both in coils. You've seen lots of pictures here of coil PEX, or as straight lengths. And in a lot of cases, buying it as a 10-foot stick or a 20-foot stick is actually more convenient to a plumber or an installer. Because if you want a nice straight run of PEX tubing going through a basement or through a wall, if you take it off a coil, you have to uncoil it first and straighten it, which isn't so bad, but it's an extra step. So a lot of plumbers are actually using straight lengths of PEX, just so that it's faster to install for them if they're doing straight runs inside a building. The straight lengths of PEX are just as flexible as the coil PEX. So you could take a 20-foot straight length and coil it up into the same diameter coil as if you bought brand new PEX in a coil. It's the same product, just packaged differently. The diameters of PEX are available from 1/4 inch, which is commonly used for ice maker tubing, all the way up to 3-inch nominal. But most manufacturers make up to 2-inch. So 1/4 inch to 2 inch is the most common size range. And there's no standard color for PEX. Most companies make it in white, but they also make it in red and blue for hot and cold water plumbing. And then some companies make a black version or an orange version or whatever color they want, really, as long as it's not yellow, because that would indicate gas. So there's a wide variety out there. When it comes to the general capabilities in terms of the pressure rating, all PEX has to be tested and proven to withstand a pressure rating of 160 psi at 73 degrees Fahrenheit. So that's a continuous use rating, and also 100 psi at 180 degrees. We showed that earlier. And most of the PEX products are also rated for continuous use at 200 degrees Fahrenheit as well. I can't imagine an application where you would actually need that. Even high temperature hot water radiators normally don't ever need temperature beyond 180 degrees Fahrenheit. But the PEX is capable of it, even if you don't really need that temperature. And there's different methods of making PEX, and you'll hear these from different PEX salesmen that will tell you, my company makes PEX A, also known as peroxide, or my company makes PEX B or PEX C. There are 3 different methods that were developed in the 60s and the 70s for producing PEX, for cross-linking polyethylene into PEX, but the letter designations are not related to any type of performance or rating system. They're just based on which came first. The first type was called peroxide, and then came the silane method, and then came the electron beam method for making PEX. So in Europe, where all of this was developed way back then, they just decided to call it PEX A, B, and C as shortcuts. A came first, then B, then C. And all the PEX tubing, no matter what methods used to produce it, has to meet the same requirements according to the standards. And a really good document that's a free download is PPI TN17. And that's kind of your handbook on PEX that'll explain the history and all the codes and certifications and standards and things like that. So it's a good document. Now, let's go back to radiant heating again. We've talked about that a couple of times. And when they started using plain PEX tubing for radiant heating in the 1970s in Europe, they thought this was the perfect material because it could withstand the temperature and the pressure, and the tubing was encased in concrete, and life was good. The problem was, a few years later, their cast iron boilers and cast iron circulating pumps, which is, back in the 1970s, 100% of everything was cast iron. They started rusting from the inside out. And it took a while for the engineers to figure out that plain PEX tubing actually allows oxygen from the atmosphere to pass through the wall of the tubing and get absorbed into the heating system water inside, and that can cause rust, which is obviously not a good thing in a closed loop heating system. Not an issue for plumbing. For plumbing, we have oxygen in our water all the time, and the water passes through once and then goes down a drain. But in plumbing systems, we don't have cast iron or steel components there. Everything is non-ferrous and can't be corroded. So for radiant heating systems or any other closed loop heating system, the engineers realized they needed to make the PEX tubing oxygen tight in some way. So they shopped around and they realized there was another type of plastic known as EVOH, or ethylene vinyl alcohol, that could actually be applied as a very thin coating or layer to the outside of the PEX tubing during manufacturing, and that would actually make the tubing oxygen tight. The EVOH coating itself, it's clear, it's transparent, you can't see it, but most of the manufacturers, when they're making tubing for heating applications today, the adhesive that holds that EVOH onto the PEX tubing itself, they normally color that, usually red, to indicate, hey, this is for heating applications, or maybe some other color. And you can see that colored adhesive under the EVOH because the EVOH itself is transparent. So this doesn't apply to plumbing applications. You don't need it there. Getting the tubing with the oxygen diffusion barrier, it's more expensive this way. And again, the barrier isn't to protect the tubing. The tubing doesn't care if oxygen passes through it. It's just like your tire leaks air over time, or you pump a balloon, and over time the oxygen leaks out of a balloon, and the balloon gets kind of saggy over time. It's the same thing with the plastic tubing. So the barrier layer there is to keep to keep the oxygen from passing through. Now, when it comes to the standards for PEX tubing, here is a group of standards that are published by ASTM and others. So ASTM F876 is the standard for PEX tubing for pretty much all of it that you're going to find. All the plumbing tubing should be marked with F876, and 99% of the heating tubing out there is marked with F876. And that standard, like I said, was published first back in 1984. Most of the products are also marked with ASTM F877, and that is the standard that's used to test the fittings and the manifolds and the valves with the tubing. It's used primarily as a standard to make sure the joining systems have good joint integrity and aren't going to leak. There is a standard for PEX pipe in IPS sizes, but it's very rarely used. And there's a new ASTM standard for the PEX tubing with oxygen diffusion barrier, but so far it's very rarely used. If you were looking at PEX tubing for a water service connection, bringing the water into a house, that is typically also marked with the American Waterworks Association number C904. That's the AWWA standard for PEX water service line. And the Canadian standard for PEX tubing, it's called CSA B137.5. So there's a lot of PEX tubing out there that's marked with F876 and F877 and AWWA C904 and CSA B137.5, all on the same piece of tubing. Earlier, when we talked about polybutylene, we talked about chlorine, and I said that now it's a requirement that all PEX tubing is tested for chlorine resistance. We recommend that you read this PPI document here to learn more about that. This is on our website, and you can download it as TN53. But the way that that testing is done, I won't get into all the details because we don't have time tonight, but it's done in accordance with an official ASTM test method known as F2023. So a lot of the tubing you'll also see marked as F2023, and that shows that that tubing has gone through the chlorine testing. That testing takes about 2 years to run and costs a manufacturer about $150,000 to run that testing. It's a very rigorous test, and they test lots of different samples at different temperatures and different pressures. But the end goal of that testing is to be able to prove that when you put that PEX tubing in potable water service, it can withstand continuous pressure of 80 psi at a temperature up to 140 degrees for a minimum life of 50 years. And that assumes that the chlorine level in the water is at 4 parts per million, which is the EPA maximum for chlorinated water leaving a water treatment plant. Nobody's water is that bad. The average in the United States is about 1.2 parts per million. But the tubing is actually tested at 4 parts per million. So it's mandatory since 2002 that all PEX tubing for potable water is tested in accordance with this test method. So that's been 20 years now that this has been a requirement. And it's a good thing that it's a requirement because it means the tubing is safe and resistant. There's also the one weakness of PEX, I should point out, is sunlight. And I always use the example, if you're a fan of Superman, you know that Superman has one weakness and it's kryptonite, whatever that is. It's from his home planet, but yet still he's susceptible to it. But when it comes to PEX tubing, the one weakness really is sunlight. PEX tubing is not intended to be left in the sun. Some PEX tubing will get damaged even just for 1 month in the sun. Laying out in the direct sunlight will actually damage the PEX tubing. And it's not going to turn to dust. It's not going to get brittle right in front of your eyes. But what happens is that an unapproved amount of sunlight exposure can actually reduce the lifetime of the PEX. So when I just said that in a hot chlorinated water environment, it should last for at least 50 years. Well, if you overexposed it to sunlight before you installed it, now you're not going to get 50 years of sunlight of chlorine life anymore. So it's actually a requirement. The PEX tubing is tested for its UV resistance according to an official ASTM test method. And this test method is known as F2657. And the details are shown here. They really do the testing down near Phoenix, Arizona, with the tubing exposed to the sun. Excuse me. It's late in the evening. We've been talking a lot today. Voice wears out. In terms of the markings you'll find on PEX tubing, those are shown here. very similar to CPVC, where you'll find the dimensions, the SDR9, the manufacturer's name, the ASTM standard, and then other codes and the temperature pressure rating will be marked on PEX tubing. In about the 5 or 6 minutes I have left here, let me get into the joining systems that you'll see for PEX, because this is important. PEX tubing is not joined with any kind of solvent, cement, or glue. It's so slippery. It has very low surface polarity, meaning it's hard to get stuff to stick to it. That's a good thing, but it means you can't glue it together. Glue just won't stick. So all the PEX fittings work on the principle of a compression seal, meaning the tubing is compressed over ribs in the fitting, or in the case of push fit fittings, there's an O-ring seal on the outside of the tubing. The materials used for making these PEX fittings, and this picture at the bottom isn't from one company. This is 8 different companies' version of PEX fittings, just put together in kind of a family picture here. The fittings used for PEX systems, they're made of either lead-free brass alloys, and that's a requirement by law now that they must be lead-free, or these engineered polymers known as polysulfone, PLS, or polyphenol sulfone, PPSU, which are the polymers that I talked about earlier. And those polymer materials are, excuse me, tested and proven to be highly chlorine resistant. Now, there's a lot of different PEX fittings out there in terms of their shapes and how they actually join to the tubing. And all those PEX fittings out there actually have their own ASTM standard to describe the materials that can be used and the dimensions and the tolerances and how the assembly takes place. So it's a collection of fittings, and they'll all have their own ASTM standard marked on them. F877, the one we talked about before, is the standard that's used to test them all for joint integrity, but then all these other numbers apply to different fittings. So I'm going to show pictures of those. One of the most popular PEX fitting systems out there, and it's been around for more than 20 years, it's described by the ASTM standard known as F1960. And it's also called the cold expansion fitting using a PEX ring. And this was pioneered by a company known as Wurzbo back in the 1990s. Now the company is known by Uponor. They pioneered this fitting, but now there's a lot of other companies make the same version of the fitting according to the same ASTM standard. The fitting body itself could be either plastic or lead-free brass. And the basic principle is you put a ring of PEX over the end of the tubing, excuse me, and then with either a hand tool or an electric tool, you expand both the tubing and the ring together to make them bigger. And then you've got a few seconds to get the fitting inside before the tubing shrinks back. And then it makes a tight seal. The other most popular type of fitting system is known as a crimp ring fitting system. And this is the same type of crimp ring fitting that was used in polybutylene, although different materials and different dimensions nowadays. So it could be a brass fitting that goes inside the PEX. And if it is, that's made to an ASTM standard called F1807. And the copper crimp ring has a black coating on it to make sure it's not a polybutylene crimp ring because they are different in dimensions. And then you can also get the same kind of fitting but molded in plastic. And if it's molded in plastic, then it's made to the ASTM standard called F2159. But it uses the same crimp ring and the same tool. Now, in some cases, people don't use a copper crimp ring. They use a stainless steel clamp with a crimp ring fitting, but instead of the ring, they're using a stainless steel clamp. And in that case, those clamps are made to a standard called F2098. There's another type of compression fitting out there that uses a stainless steel clamp, not the banded clamp, but in this case, it's more of a stainless steel cup that gets compressed over the fitting. And these fittings were pioneered by a company called Vega out of Germany. And they could be made of polymer or bronze material on the inside. And then there's also the push fit fittings. The push fit fittings that are developed for use with copper or CPVC also work equally well with PEX as well. And those fittings can be made out of brass or a polymer material, the same type of polymer material that the other fittings are made of. So it's a wide variety of fittings. And then you can get valves with those PEX ends directly in the end of the valve. So for plumbing systems, you could have PEX coming out the wall to a quarter turn stop below a sink or a toilet. And then in a lot of cases, what people will do in plumbing systems is they transition from PEX to copper inside the wall with a copper stub out And then you have copper coming out the wall where you could use a regular compression valve, but it's actually most of the plumbing inside the wall is actually PEX. The most important thing to point out, and then I'm done, is that not all PEX fittings are approved for use with all PEX tubing. Each tubing manufacturer will actually test the fittings that they want to endorse with their tubing to make sure that they're completely compatible. And then they'll go ahead and mark that ASTM number on their tubing if they recommend it for use with their tubing. So in this example here, the white tubing at the top, you can see all the markings on the PEX. It's marked with F876 and F877, 2023 for chlorine testing. And then it's marked with F1807, which is the crimp ring fitting, F1960, the cold expansion fitting, and F2080, which was another type of cold expansion fitting, marked right in the tubing to show that it's compatible. And there's different manifolds, but that brings us to the end of PEX. And then we have a few slides here on industry resources. We invite you to go to the website. You'll find a web page on each of the materials that we talked about tonight. We have a calculator for doing pressure loss sizing. We've got different versions of presentations on our website, some recorded ones and some slides you can download. And that's it. So I think that's my hour's up. We got through all our sections that we wanted to get through. So thanks for the time, and I can stick around if there's any questions, Hollis.
Okay, Lance, what I'd like you to do is, if you could turn off your screen share, leave that up there for just a second so people can capture your information, but then turn off your screen share so I can share mine. And then we're not going to have time for a lot of questions, but I would like you to address the one question that we frequently hear about CPVC becoming brittle over time. Could you address that? Well, that'll be the only question for this evening.
Yeah, sure. And that is a reality. That really does happen. Once CPVC gets to be about 10 years or so old, it does start to lose its flexibility. When it's new, it's a really flexible material, and it can withstand water freezing into ice and expand its diameter and normally absorb that. But once you get 10 years old or older, it loses some of its ductility. It's still perfectly okay to stay in service. It will withstand the pressure for 50 years or more. But the consequence of its losing its ductility is that if you bang it with a wrench, let's say it's in the mechanical closet and you're changing the water heater and a wrench slips and you bang the piece of CPVC with your wrench, it could actually crack and break. So if that happens, it doesn't mean that the whole CPVC plumbing system has gone to crap. It just means that don't hit it with a wrench, don't bang it. Even when you're cutting old CPVC, they don't want you to use just a regular shear for cutting old CPVC because the shear will actually cut it off and crack it. What you really should use is a copper tube cutter, a wheel, and slowly go around the old CPVC with the wheel cutter to slowly slice into it. So that's the main information I have on that one. Good question.
Right.
Thank you.
Right. That's real helpful, Lance. Thanks a whole lot. That was a real good presentation.